So let's go ahead and get started. So as I mentioned, my plan is to just kind of go over lecture content, kind of summarize and review everything, and then try to answer any questions that you have about homework problems or lecture or anything else, basically. Okay. So just as an overview of everything that is potentially going to be on the exam. So for one thing, there's a little bit of fluid mechanics that we had left over, which was talking about viscous flow, and then moving on to completely separate set of topics. So we talked about oscillations or simple harmonic motion, and then a whole bunch of different topics under the umbrella of waves. So we talked about sinusoidal traveling waves. No, Bernoulli's nothing about ideal fluids is going to be on the exam. Sinusoidal traveling waves. We talked about sound, light, intensity, and intensity level. And then superposition and standing waves. And finally, interference. Okay, so that's kind of very broadly all the topics. Let's go through everything one by one. So starting with viscous flow. And there's basically only one equation here, which is our viscous flow equation or Poiseuille equation. So suppose we have a tube with a constant radius. I've gotten several questions from people about, how do we treat the case where the radius is not constant? We actually can't using the formula that we have. And it would actually be, in general, a lot more complicated to try to account for the radius of the tube changing. So Poiseuille's equation is only for the specific case where the radius stays constant. So we have a fluid flowing through our tube, okay, with a certain radius. We're looking at a segmented tube with length L, and we have a flow rate Q through the tube. And if the viscosity, in terms of the viscosity of the fluid, the pressure drop across the tube, right? We're going from high pressure at this end to low pressure at this end, with the pressure dropping in the direction of the fluid flow. Okay, we have this equation. Okay, and that's pretty much it. The only sort of complication to this, which I mentioned in an example in lecture, and which you saw in the homework, is if you have for example, in the circulatory system, if you have a situation where you have a tube that's branching off into smaller tubes, remember the continuity equation still applies here. So, if we have a certain amount of fluid flowing in, and we have, you know, some fraction of the fluid flowing out through each of these branches of the tube, then the total flow rate out has to equal the flow rate in. So, for example, in the circulatory system, you have large blood vessels that branch off into smaller blood vessels. The flow rate doesn't stay constant. The flow rate's changing because you're, some fraction, if you look at, for example, the arterioles versus the aorta, right? It's only some tiny fraction of the total flow through the aorta that's making it to each arteriole. So you need to work out, what the flow rate is in each branch of your tube in order to work out what the pressure drop is across that specific part of the tube. But other than that, I mean, this is pretty much just an equation that we can plug into. Right, you might use it to find the pressure drop, or if you know the pressure drop, you could use it to find the flow rate, like you saw in the discussion worksheet. But that's basically it as far as viscous flow, right? And this is, I guess I'll just say, this is in contrast to ideal flow, right? So viscous flow, I've also gotten a lot of questions about this. Right, so there's two kinds of flow that we've studied in this class. Ideal flow, which is the one where Bernoulli's law applies, and viscous flow, which is the one where Poiseuille's law applies. Okay. Those two are, or I should say, an ideal flow means a flow without viscosity, where we're neglecting viscosity. So these two will never appear together in the same problem. Would we be asked to find the pressure from Q in to Q1? I'm not sure what you mean by that. You could be asked, like if this were a constant radius here, you could be asked to find the pressure drop from here to here, but you couldn't be asked to find the pressure drop from here to here because that's not a tube with a constant radius. So this equation wouldn't apply. Okay. Moving on then. So next we talked about simple harmonic motion. Right, the idea here is we have something like a mass on a spring or a simple pendulum. And we get this repetitive or oscillatory motion. And simple harmonic motion is specifically what we get when we have a linear restoring force. And that's the only force acting on our system. Okay, so for example, the spring force. And in that case, what we get is sinusoidal motion, right? So we found that, sorry, someone's calling me. Okay. What we get is a sinusoidal motion, like this. Okay. Oops. So, and when I say it's sinusoidal, I mean if we plot the position as a function of time, we get a graph like that's sinusoidal. So we want to write down the position as a function of time. That would look like this. Okay. So A here is the amplitude. Which is the maximum displacement of the system from equilibrium. Omega is the angular frequency, which is 2 pi over the period. Right? The period being the time it takes for the motion to repeat. So in terms of the graph, we could pick any point on the graph and ask how long does it take the motion to get back to that point. In particular, we could look at the time between like peaks on the graph. Okay, and omega is telling us the rate of repetition, right? This is also related to the ordinary frequency. Omega is 2 pi times f. And then phi naught is the phase constant. And this is related to our initial conditions. So what's the initial position? What's the initial velocity? All right, now we talked about the idea that this cosine function, it's a function of an angle. That angle we call the phase. All right, and how should we interpret that angle? It's not a real physical geometrical angle that we can measure with a protractor, but we can give it a physical interpretation, which is we have this picture where we can draw what we call a phase diagram. Where we have a point moving around in uniform circular motion, okay, moving around counterclockwise. And if we project that motion down to the x-axis, okay, then we get simple harmonic motion. And the angle this angle here of the particle measured from the x-axis, that is the phase. So as you can see, as time increases, right, our phase is going to be increasing as well. And that corresponds to the fact that our particle is moving around the circle. Okay? And as it moves around the circle, our particle, the projection of that is moving back and forth along the x-axis, oscillating back and forth. Okay. So simple harmonic motion is the projection of uniform circular motion to one dimension. All right, so this is the position as a function of time. Now we can also write down the velocity as a function of time, just by taking the derivative of x of t. We get minus omega a sine omega t plus phi naught. And from this, right away, we get the maximum speed is omega times a. All right, and then once we have these written down, then we can write down a formula that allows us to calculate the phase constant from the initial conditions. namely this formula. Okay. So given that we know v naught x and we know x naught, we could plug into this formula. Now we're not always going to know both of those. So we could determine the phase constant in other ways. For example, if we know x naught, then we could plug in 0 to our position equation, and this gives us an equation also for phi naught, right? And you would have seen this on the homework and on the discussion worksheet. For the v naught equation is, or sorry, for the tangent equation, is v naught a scalar even if the object is moving left? No, v naught x is the x component of the velocity. So I mean, it is a scalar, but it has a sign. Right? It's negative.
So v naught is not speed in this case. It would be velocity if you put in the equation.
Well, if I wrote v naught, that would mean initial speed, but I'm writing v naught x. So it's the initial x component of the velocity.
Okay, so if it was moving left, the top would become positive.
Would be, yeah, v naught x. If we're moving left, then
Yeah.
v naught x would be negative, and this would be positive. Yeah,
Okay, thank you.
yeah. Okay. So we also talked about energy conservation in simple harmonic motion. Right, this is typically the approach you want to take if you have a problem that's asking you, what's the speed of your system at a certain point in space. Generally, the idea is you want to use energy if you can, because it's usually easier than using kinematics. And when can you use energy? Basically, it's any time you have a problem that's not asking you for the time at which something occurs or the time something takes. For that, you'd need to use kinematics. But if you're just trying to find the speed, you're just trying to find the position when the mass has a certain speed or something like that, you probably want to try to use energy conservation. And so how do you do that? Well, the total energy is kinetic plus potential. And we can, this is constant, right? Because the energy is conserved. So we can evaluate this at any point in the motion. So we could evaluate it when the mass is at the maximum displacement, when it's at the amplitude, and we'd get this expression. Or we could evaluate it when the mass is at equilibrium, moving with the maximum speed. And whatever we calculate for the total energy at any point in the motion, it has to be equal to that for every point in the motion because it's conserved. Right, and so this is useful, if you know like the initial speed, the initial position, and you want to know like what's the amplitude of the motion or something like that. Let's say you know the amplitude and you want to find what's the speed when the mass is at a certain position, then you could use energy conservation. Okay. Another thing we talked, so we talked about, how do we determine what the angular frequency of the motion is? right? That we get from, well, we write down an equation that looks like this. Anytime we see an equation like this where we have the second derivative of the position is equal to minus some constant times x, or the second derivative is the same thing as the acceleration. So acceleration is minus omega squared times x. This tells us that we have simple harmonic motion. And in particular, it's simple harmonic motion where the angular frequency is omega. So if we do this for a mass on a spring, we write down the equation, what we end up getting is that omega is square root of k over m. And if we do it for a simple pendulum, with length L, then we get that omega is square root of g over L. All right, and then if we wanted to, we could go ahead and calculate the period, 2 pi over omega, or calculate the frequency is 2 pi times omega, etc. Okay, give me 1 second. I think there's like a cable, my monitor cable is loose or something because it keeps switching off. Give me just 1 sec. Okay, hopefully that fixed it. All right, sorry about that. Any questions about any of this stuff? Okay. Let's see, I think that's everything. All right, moving on now to waves. So we started off talking about the example of traveling waves and specifically sinusoidal. Actually, let me take a step back. Before we zero in on sinusoidal waves, let's just talk about traveling waves in general. So remember, a wave is this collective motion created by all the particles in a medium moving together, at least if we're talking about a mechanical wave. It's different if we're talking about electromagnetic waves, but let's put that aside for now. It's this collective motion created by all the particles working together. So the wave speed doesn't have anything to do with the motion of the individual particles in the medium. So, if we imagine a wave on a string, right? We could create, like I try to do in lecture, we could create like a pulse on a string that travels along the string. Okay, something like this. You get the idea, right? And the idea is the wave is this pulse, okay? It's this collective thing that is moving horizontally along the string. But notice the particles in the string, if we were to zoom in on like the atoms in the string, they're not moving left or right. They're only moving up or down, right? So, if you focus on one particle, let's just say like this one here. Okay, doesn't like me doing that. It's only ever moving up or down. Okay. So the actual motion of the wave is disconnected from the motion of the particles. I mean, the wave is created by the particles moving up and down, but that's not actually what the wave motion is. It's this pattern of motions of all the particles together moving along the string. So that's the wave. And then the velocity of the wave, which is set by the medium, by the material carrying the wave, is the velocity of like this pulse, this collective motion of the particles moving along the string. Okay. And that's independent of the velocity or the speed at which the particles move up and down. All right. It's another thing I've gotten questions about, so I wanted to try to clarify that. All right. So we've got a wave on a string or in any other medium created by particles moving. It can be a transverse wave like this, where the particles are moving perpendicular to the wave. Or it can be a longitudinal wave like in a sound wave. Where the particles move parallel to the wave. Okay. Is the wave speed of a string constant even if the frequency changes? Well, the frequency is set by the source. I think we've gone back and forth on this quite a few times, but the wave speed the wave speed and the frequency are completely independent of each other. Now, whether the wave speed is constant is going to depend on what's happening to the string, right? If you're changing something about the string, like you're changing the tension or you're changing the the density, then the wave speed could change, but that'll be changing. Changing the frequency doesn't affect that. Yeah. So what does set the wave speed? For a wave on a string, okay, it's the square root of the tension divided by the mass density, mass per unit length. M over L. Okay. All right. So now let's think about the particular case of sinusoidal waves. I guess I'll mention one more thing before I do that. So if we want to plot a wave, right, in the sense of drawing like a one-dimensional graph of the wave, there's two ways to do it. we can plot the displacement of our string, or the displacement of the wave, at different positions at a single instant in time. Okay, so that would be like if we were to take a picture, take a snapshot of the wave. Or we can make a history plot, which is we pick a single point along the string and we plot that over time. So in other words, we make a position versus time graph for that specific point. Okay. All right, now for the particular case of sinusoidal waves, right? And again, this is traveling waves. We'll get to sinusoidal standing waves later. Our displacement is sinusoidal. So it's a sinusoidal function of both x and t. Okay, so I put the plus or minus here. The plus sign, maybe I'll do this. The plus sign is for a left moving wave, or in other words, a wave moving in the negative x direction. The minus sign is for a right moving wave. Okay, A here is the amplitude, so that has the same interpretation as in simple harmonic motion, where it's telling us the maximum displacement of our string. K is the wave number, which is 2 pi over the wavelength. Maybe let me do this. Right, if we draw a snapshot plot, so we plot y versus x, then here's the wavelength. Right, we can interpret that as the distance between the peaks. And then k is 2 pi over that. And we call that the wave number. Okay, omega is the angular frequency. That has the same interpretation as in simple harmonic motion. And indeed, each point, if we have a sinusoidal wave, each point is moving in simple harmonic motion. And we know it's simple harmonic motion because if we make a history plot, position versus time graph for each point, then we get a sinusoidal graph. So the period of the wave you can interpret as the period of that simple harmonic motion. It's the time it takes for that motion of the particles to repeat. All right, and then phi naught is a phase constant, just like in simple harmonic motion. This tells us the initial condition. So what is our wave doing? What's the displacement at x equals 0 and t equals 0? All right, and we have this relationship for any sinusoidal wave. So it doesn't have to be a traveling wave, could be a standing wave as well. The wave speed is equal to the wavelength times the frequency. So this is the wave speed, which is set by the medium. The frequency is set by the source that's generating the wave. And then lambda depends on both those things. Yeah, so that's what I'm saying here. So is the frequency of the particles in the wave the same as the frequency of the wave itself? Yeah. So the period of the wave is the period of the simple harmonic motion of the particles. Okay. So we talked about sound waves. Now, sound waves, they don't have to be longitudinal, but if we're talking about sound waves like in air or in any fluid, they are longitudinal waves. And we can think about the variation that we have as being a variation in the pressure in the medium, where when we have regions where the particles get more spread out, the pressure goes down, and when the particles get compressed together, the pressure goes up. A light wave is something, well, not completely different, but something that is much harder to describe than the other types of wave. It's a wave in the electric and magnetic fields. Okay. And when I'm saying light here, I really mean any electromagnetic wave, so that it could include, microwaves, radio waves, X-rays, etc. Okay, a light wave doesn't, or an electromagnetic wave, EM wave, doesn't require any medium to propagate. So it's not a mechanical wave. All it requires is electric and magnetic fields, which exist everywhere throughout space. And a light wave, at least in vacuum, travels at the speed of light, which is about 3 times 10 to the 8 meters per second. Okay. Right. So from here, we went on to talk about intensity. Right. So this is a way of, intensity is a way of quantifying the energy carried by a wave. So it's the power per unit area. Okay, I'll use a fancy A for the area so we don't get it confused with amplitude. And what's the area here? Well, now we're thinking about, instead of a wave moving on a string, like a one-dimensional wave, we're thinking about a wave being produced by, a source like a speaker or a light bulb that is propagating in 3 dimensions. So as it spreads throughout space, it's spreading out, for example, over the surface of a sphere, or the wavefronts of the wave are spheres. All right, so in this situation, right, if we observe the wave, say we're here observing the wave distance r from the source, then the intensity we would receive is the power divided by 4 pi r squared, because that's the surface area of a sphere. Okay. Right, and then if we wanted to know how much power we get, we would just take, let's say we had a microphone or something, we want to know how much power was being supplied to that microphone by the wave, we could just take the intensity at our location and multiply it by the area of, the receiver, the diaphragm of the microphone. All right, we can also, instead of measuring the intensity directly, we can also use the sound intensity level, or in general intensity level. This is used for other types of waves as well. Okay, this is effectively just the logarithm, base 10 logarithm of the intensity. So I naught here is a reference intensity, which is conventionally chosen to be 10 to the minus 12 watts per square meter. All right. And then I guess last thing here, we talked about the Doppler effect. So this is a change in the frequency due to motion of either our source or our observer relative to the medium carrying the waves. And the idea is, if we have, let's say we had a moving source, okay, and like stationary observer. Well, the source is emitting waves. Okay, something like this. I'm trying to get the wave fronts centered on the source. Not doing the best job. Here, let's do this. Okay. I'll put them closer together. That'll make it easier. All right, as the source moves, it emits waves, and these wave fronts spread out. And we can draw, successive wave fronts centered on the source at each instant in time. Sorry, it's a little bit hard for me to draw this with my tablet here. Okay. Pretty bad, but hopefully you get the idea. Right, as our source, let's say our source is approaching our observer like this, then in the direction the source is moving, these wave fronts are going to be spaced closer together. And in the direction that the source is moving away from, the wave fronts are going to be more spread out. So the distance between the wave fronts, right, this is the wavelength. Each one of these, imagine that I drew this better and these were all equally spaced. These are each the wavelength, right? And this is the wavelength over here. So in the direction the source is moving, we get a larger wavelength. In the direction it's moving away from, we get, or sorry, other way around. In the direction the source is moving, we get a smaller wavelength. And in the direction the source is moving away from, we get a larger wavelength. Okay. So that means if you're the observer here and you're in the direction the source is moving toward, this, then you're going to see a smaller wavelength, which means you're going to get a higher frequency, or higher pitch. And if you're over here in the direction the source is moving away from, then you're going to get a larger wavelength, which means a smaller frequency, lower pitch. That's if the source is moving. Now this also works if the observer is moving. So let's say our source is here and just not moving, emitting waves like this. Okay. Well, now if you're the observer and you're moving toward the source, let's say, then you're going to encounter those wave fronts faster than if you were just stationary. So you're going to be hitting more wave fronts per unit time, which means your frequency is going to be higher. If you were moving away from the source, then you would see you're like outrunning the wave fronts, or you're moving opposite the direction that the wave fronts are moving. So you're going to be seeing fewer of them per unit time, and you pick up a lower frequency. Why isn't the wavelength constant? Because the wavelength is like the distance between the peaks in the wave, and because the source is moving, those peaks are going to be moving closer together in the direction the source is moving. They're going to be moving further apart in the direction the source is moving away from. Okay. So anyway, point of all this is we can calculate a different frequency. So the shifted frequency. What is it? Hold on. Okay. Can never remember which one goes on top and which one goes on the bottom. Okay, it's the observer on top. Sorry, this is my first time actually teaching the Doppler effect in this class, so I don't have it burned into my memory. Okay, so if this is the frequency output by the source, the Doppler shifted frequency is this. Okay, VO sub x is the component of the velocity of the component of the observer's velocity. In the direction the source is moving. Or sorry, not in the direction from the source to the observer. So our x direction is the direction from the source to the observer. Here, this would be x. Here, this would be x. And Vs sub x is the velocity of the source with that same orientation. Okay, and you can see that, if the observer is moving away from the source, then we'll end up with a lower frequency. If it's moving toward the source, we'll get a higher frequency. And if the source is moving toward the observer, we get a higher frequency. Source moving away from the observer, we get a lower frequency. Okay. Moving on now, we talked about the fact, so first of all, the superposition principle. Which is really as simple as saying that waves add. In other words, if we want to get the total displacement for a wave, we add the displacements of the individual waves. Okay. And one consequence of this is interference. So when we add waves, then we can potentially end up with the superposition having a higher or a lower intensity than the waves that we added. All right, and one manifestation of this is if we take two traveling waves moving in opposite directions, then we get a standing wave. a standing wave is a wave that has nodes and antinodes in fixed positions. So like one example of this would be a wave on a string where we have the ends of the string, which are like fixed in place. Those act as nodes. The nodes are the positions where we have no displacement. And then the antinodes are the positions where we have maximum or minimum displacement. If a standing wave oscillates in place, why is there a wave speed? Because again, the wave speed is a property of the medium. It's not a property of the wave. So even though the wave is not, so there's two ways to think about it. Number one, the wave is not moving back and forth, right? But the string still has a wave speed that it would carry traveling waves at. Now, the other thing is that we get the standing wave by superimposing two traveling waves, right? So in that sense, it is actually moving. It's not one moving wave, but it's two moving waves.
But if there's no like X displacement, how do we calculate like how much it moves? Because if it's just going like up and down.
How do I guess I'm not sure what you mean by that. How do we calculate how much it moves?
Because isn't like the wave speed the movement in the X direction, but if there's no like movement in the X direction, like horizontal movement.
But there is, right? So we have two waves moving. We have one moving right and one moving left, and we add them to get, when we add them together, we get this standing wave. So the speed at which those two waves are traveling along the string that we add together, that's the wave speed.
But how do we determine that from like looking at the, I guess, the diagram?
Well, we determine that from, like, let's say you had a graph like this, right? Like a snapshot graph or a series of snapshot graphs. If you know the frequency of the wave, then you know the wavelength from the standing wave pattern, and from that you know the wave speed.
Or would the wavelength be from like the individual waves, like the two waves, or like the sum of it?
It's both. So when
Oh,
we add two waves with the same wavelength, and we get a standing wave with the same wavelength.
oh, okay. I see. Thank you.
Yeah. Okay. So one example of this is standing waves on a string. Okay, where the ends are fixed. So the ends are nodes. Oh, let me just, one other thing I want to mention. In a standing wave, the nodes are half of a wavelength apart. I guess that's another way that you could measure the wavelength and measure the wave speed is you just measure the distance between nodes, and you know that that's half of a wavelength. And the antinodes are also lambda over 2 apart. It's like this distance here. This is half a wavelength. This is half a wavelength. Okay. So if we have a standing wave on a string where the ends are nodes, there's only certain wavelengths or frequencies of the standing wave that we could have. Which are given by these equations. M here is any whole number. We can also have standing sound waves. In a pipe. If we have a pipe with two open ends, we call an open-open pipe, that has the same harmonic content as a string with two fixed ends. Okay, if we have an open-closed pipe, right, so this would be like, we'd have standing wave patterns like this. Okay, so this would be like m equals 2 because we have two antinodes, right? We have a one full wavelength fits within the pipe. The other case would be an open closed pipe. That would be like this situation. Where we have a node at this end and then we have an antinode at the other end. Something like this. Okay. And in this case, we only get odd harmonics because we need to go from a node at one end to an antinode at the other end. So here this would be like n equals 3. And we get frequencies that are like NV over 4L, wavelengths that are like 4L by N. So we need an odd number of quarter wavelengths to fit inside the pipe, right? And I'm using N here as opposed to M to indicate that these are supposed to be only the odd numbers. Okay. All right, and then we talked about interference. I think I might just stop there for the moment and just pause and ask you if you have any questions because I was expecting to get done with this sooner and I want to make sure that you have some time to ask questions. So I can go over the interference if you want, but maybe let me just see if anybody has questions about anything they want to ask. Why is the harmonic 2 and not 3 for open-open? Are you asking about like this specific picture? Why is this m equals 2? So m is, you can think about for an open-open pipe, m is like counting the number of antinodes. So I have one antinode here, one antinode here, so this is m equals 2. Right, and that's also true here, right? This is 3 antinodes, so this is n equals 3. Okay, yeah, I'll do the interference real quick. So we talked about interference, whether we have constructive or destructive interference is determined by the phase difference. between two waves. Right, so remember, constructive interference means we get we get the maximum amplitude or intensity. Destructive interference means we get the minimum or zero amplitude or intensity. To determine whether we have constructive or destructive interference, we want to write down the phase difference between our waves, which is going to be k times delta x plus delta phi naught. So this is the phase difference due to the path length difference. And this one is the phase difference between the sources. Okay, so delta x here is the path length difference. Which means the difference in the distances that the waves have to travel from the source to the observation point. And k is, of course, the wave number. And then delta phi naught is just the whatever phase difference might exist between our sources. If they're in phase, there's no phase difference. If they're completely out of phase, we'd have a phase difference of pi, and we can have anything in between. All right, so then if we want to determine, or the condition for constructive interference is that our phase difference is an even multiple of pi, 2m times pi, and the condition for destructive interference is that our delta phi is an odd multiple of pi. Okay, that's pretty much it for that. Okay, let me do the chat questions and then I'll get to your hand raises. So if the string is vibrating at the fundamental frequency, does that mean sound is also at fundamental frequency or just the same frequency? Is the m of sources traveling through two different mediums the same if they have the same frequency? Let me let me try to parse that out. If the string is vibrating at its fundamental frequency, does that mean sound is also at the the fundamental frequency of what? The fundamental frequency of the string?
I guess so for example, if you plug a guitar string and then there's a frequency and it gets transmitted to like a tube, and then that's also vibrating at the same frequency, how do we know what the M is of that if we know what the M for the string is? Like are they
No, it may not be, it may not even be one of the M's for the tube. It's just the sound wave has whatever frequency. This again, the frequency is set by the source. So the source in this case is the guitar string. The frequency of sound in the tube is the frequency, the fundamental frequency of the guitar string. That may not be one of the harmonics of the tube at all. Now, if it is, you could calculate what the harmonics of the tube are and see if that matches up with the frequency of the guitar string. But it doesn't have to be related to the harmonics of the tube at all.
okay, so if the harmonics of the string is 2, and then say the frequency is like 10, and then the tube would also have a frequency of 10, but the harmonics of the tube wouldn't be necessarily 2.
Yeah, so let's say like, sure. So let's say the frequency is 10. The harmonics of the tube might be, 3, 5, 7, 9, 11. And so maybe the frequency of the sound does not match up with one of the harmonics of the tube.
Then would the tube still be able to have that frequency?
Well, there would still be a sound wave. It just wouldn't resonate with the tube.
Oh, I see.
So it wouldn't set up a standing wave inside the tube. But you'd still, if you placed a microphone somewhere inside this tube, you'd still hear that sound.
Oh, okay, so the equation like Fn equals like NV/4L is only for standing waves. Like if it's not resonating, you can't use that.
That's right. Yeah.
Okay, I see. Thank you.
Yeah. Can an open tube have an odd number of antinodes? Yes. So you could have, like, here's an open tube. Here's m equals 3. Oops. Right. Something like this. So 3 antinodes, m equals 3. Alicia?
Yeah, I had a question about one of the textbook problems.
Okay.
Can I share my screen to show it?
Sure. Go for it.
Okay. Mm, Can you see the problem?
Yeah.
Okay, yeah. I just had a question about this. I'm not too sure how to proceed with this.
Yeah, this is hard. I'm not going to make you do this. I would,
Okay.
I specifically decided not to ask you to do this ever. So,
Oh, okay.
yeah. So, I mean,
All right.
the way to do it, you have to kind of um, like work backward in time where you,
Yeah.
yeah. Um, yeah, I'm just gonna leave it at that.
Okay. Yeah.
Yeah.
No worries. I just wanted to know because like I know we went over like converting between history and not converting between, but like we went over how to like create history and snapshot graphs in class. So I thought this could potentially come up, so I wanted to make sure.
Yeah, I'm not gonna make you like take a history graph and turn it into a snapshot graph. You should be able
Okay.
to, I mean, you should understand generally what a snapshot and history graph, what those are. And I would
Hmm.
say, be able to draw them from, if I write down like a sine function, with the wavelength and the frequency or whatever, you should be able to draw graphs from that. Um,
Oh yeah.
but yeah,
All right. No worries. Thank you so much.
sure. Okay. Um, Janice, so can I show how I would use a phase diagram to determine the phase constant for a wave? So like for the worksheet problem, for example. Sure. Okay. So, I mean, I pretty much I explained this one in the worksheet solution, but I can just go over that again. So we have this mass on spring. At t equals 0, the spring is not stretched or compressed. So our x initial is 0, and the mass is moving to the right. So we have a positive x component of our velocity. All right, now what we need to do is, so in this case, it's relatively easy because we know x naught is 0, right? But, maybe we have some, so, maybe you're given x naught, and then from x naught, you want to determine, what the phase constant is. Or, you have x naught and v naught x, and you want to do the inverse tangent formula. Okay, but either way, when you do this, you're going to get two possible answers, right? And even in this problem where we know x equals 0, we get two possible answers. So those answers are, here's one point where x equals 0, and here's the other point where x is equal to 0. Okay. And so we need to use the velocity to determine which of these points we want. All right. And the problem tells us that the mass is moving to the right initially. So remember, when we draw our phase diagram, the point in circular motion is always moving counterclockwise. So we draw our velocity on there like this. At the top here, when the angle is pi over 2, then our mass is moving to the left. And over here, when the angle is 3 pi or minus pi over 2, 3 pi over 2, the mass is moving to the right. So because I know my initial condition is the mass is moving right, this is the one I want. So my phase constant here I know would be minus pi over 2. Right, and in general, let's say I used the inverse cosine equation, and I had the value of x is whatever, 0.6 times the amplitude, right? So I'd have 2 points here and here. And again, I'd need to use the direction of the velocity to determine which of these 2 points I wanted. Okay. Hopefully that helps. Sure. Shaheen?
I think Daphne had their hand up before I did, so if you don't mind, they can definitely go first.
Did you have another question, Daphne?
Oh yeah, sorry.
Okay.
I just had a question. Like, I don't really understand what in phase means. Does it just mean that they're starting at the same position? But if they're one's going up and one's going down, does that count as in phase still? If they're I guess when t equals 0, they're at the same position.
So what is in phase? What are we saying is in phase?
Like the two waves.
So if the two waves are the two waves being in phase means that they're both at the same point in their cycle at whatever point we're talking about. So trying to figure out how to draw this.
So does in phase mean constructive interference? Or
Well, if we have two waves at the same point in space and they're in phase with each other, then they'll interfere constructively. Yeah, that's true.
oh, okay. But say could one be going up and the other one be going down, but they're just at the same point? Does that still count as in phase?
No. So they have to be, right? So it's, if I draw a sine graph,
Yeah.
right? The two waves, I don't know how to draw, let's say one of them is at this point in its cycle. In order for them to be in phase, they would both need to be at the same point, right? You couldn't have one here and one here. So in phase means they have the same phase, right? They're at the same point along this graph.
Oh. Okay, so does in phase mean overall, the delta, we're just talking about the source? I don't understand, does in phase mean the entire equation is in phase or just the
It depends. It depends on whether we say the waves are in phase or the sources are in phase. So if the sources are in phase, that means that when the waves start at the source, right? If we compare the phase of the waves at the two sources, they're the same. But they're not necessarily going to stay in phase as the waves travel. The waves won't stay in phase as they travel. If we say the waves are in phase, then we're saying at some particular point in space, then the waves are at the same point in their cycle at that point.
Or wouldn't they just stay in phase? Like if nothing changes, then why would
No,
they?
no, because let's say we had like this is one source and this is a second source, and the waves start in phase. Right? You can see they start at the same point in their cycle. They both start at, y equals 0. But if we look at any point along here, they're not at the same point in their cycle. They don't line up with each other. So because they're traveling different distances, they become out of phase with each other.
Oh, I guess I wouldn't consider that in phase then. So just I thought in phase means that they have to be like exactly lined up. What is
So
that? Is
the sources are in phase here. The sources are in phase. The waves are not in phase. So they start in phase at the sources,
okay,
but
but if
then
the sorry phase, they should always be in phase then.
say that again.
But if the waves are in phase, does that mean that it'll just stay in phase then? Or
No,
would
because they could be in phase at one point and out of phase at a different point. Like if these are my two sources and my sources are in phase with each other, then let's say I have, the waves travel like this. At this point here, the waves will be in phase, but at this point here, they'll be out of phase.
oh, but how do we
So
know if phase or not? Like at that point.
well, we calculate delta phi. Right?
Oh,
That's the whole point. If we want to
if
determine whether they're in phase or out of phase, we need to write down the phase difference and then check whether this is an even multiple of pi or an odd multiple of pi.
okay, I see.
Okay.
Thank you.
Yep. All right. Go ahead, Sheen.
Thank you. I just had a question about the problem bank, specifically question number 33. Um, or actually, wait, forgive me, 34. I figured it was Doppler effect, but I honestly just wasn't sure how to set it up. I didn't really know where I would be taking as like delta x versus taking point A and point B, and it all kind of gets confused in my head.
Okay. I don't think there are any Doppler effect problems or there definitely aren't any Doppler effect problems on the problem bank. So,
Gotcha.
34, you said?
Yes.
Yeah. So this is an interference problem, right?
Okay, that makes okay.
Which is why it's, yeah.
I might just
So,
give it a try with interference stuff.
okay.
And then maybe get back to you. Thank
Okay.
you.
Sounds good. Yeah. Okay. Um, let's see. Problem 4 on homework 7. Okay. Okay. So what have you tried? Here, let me pull up the problem. So we've got two speakers a certain distance apart. So it's an interference problem, right? So the setup for all these problems should be the same. We know that we want to look at the phase difference. So Victor standing over here somewhere. Okay. And the problem doesn't tell us this. It should. The intent here is that the two speakers are in phase with each other. So there's no delta phi naught. All right. And what we're saying is that initially this is destructive interference, right? It says Victor hears no sound at the initial frequency. So with whatever our initial lambda is, this is destructive interference.
So I had a question, like, how do you know that it's destructive? Like, couldn't it be that it's like constructive? Because aren't there also points on constructive interference where the amplitude is like zero? Like, I
No,
guess,
constructive interference means that the amplitude is maximum. So if he hears no sound, that has to be destructive interference.
but like, wouldn't the like when the constructive waves like add up, aren't there also points where the like the amplitude is zero because both are zero?
There may be points where we're talking about the specific point where Victor is standing. There may be other points away from where Victor is standing where there's different interference, but we're talking about at this one specific point.
Oh, but how do we know that point isn't a point where like the amplitude is just zero for the constructive interference?
There's no such thing as constructive interference means that we get the maximum amplitude. We get a non-zero amplitude. There's no if your conception of what constructive interference means includes there being no amplitude, then something's getting mixed up somewhere. Constructive interference means we have to get some intensity.
Oh, because I'm just thinking like if the two waves like aren't there like if they're in phase and they're like summed up, like aren't there some points where both of the waves are zero? And then in that case, wouldn't the sum still be zero? So how do we know that Victor isn't like standing at one of those points?
No, there are no points. So here's what constructive interference means. Right, let me yes. Sorry, give it a second. Okay. I'll just draw it. Constructive interference means that the two waves are lined up with each other like this. So when we add them together, right, we get something with a larger amplitude like this. There's never, so they have to be exactly lined up like this in order to have constructive interference. There's never going to be a point where you have constructive interference and the waves aren't lined up with each other.
Oh, but I see this like diagram. Can I share my screen?
Sure.
Mm. Like I was looking at like this diagram.
Yeah.
Like there are points like for example right here where like it's like I guess like 0. Like this point right here.
Yeah.
So I'm wondering like
Where the displacement is 0, right?
yeah.
But the amplitude is not 0.
Wait, what's the difference between that?
The amplitude, so the wave is a bunch of particles like moving back and forth like this, right? But the
Yeah.
fact that they're moving back and forth means that they're, if they like collide with your ear, then they bump into your ear and you hear something, right? If they're not moving at all, then you hear nothing.
Yeah.
Now, the fact that they move back and forth, sometimes they're in the middle. Sometimes they're over here, sometimes they're over here, sometimes they're in the middle. But the point is they're moving back and forth. So the amplitude is, what's the range of that back and forth motion? And that's what determines how loud the sound is that you hear. And if they're not moving at all, that means 0 amplitude and no sound.
But what does displacement equal 0 mean then? Like for example, at this point?
It means that there's no motion of the particle. It means that the particle is at its equilibrium position at that point.
So wouldn't you
Okay,
not
I need to go because I have my other review session. Let me just quickly answer that person's question about the homework. Okay, so you set up your delta phi, you have this, it's destructive interference because Victor hears no sound. And then you triple, so you can write this in terms of the frequency. Okay, and then you increase the frequency. So then as we increase the frequency, it's saying we get another point. So the sound goes loud, soft, loud, soft, loud. So as we triple the frequency, as we go from the original frequency to 3 times the original frequency, we start at a point of destructive interference at some value of m. We get another point of destructive interference at the next higher value of m, and then we get a third point of destructive interference at another higher value of m. And so you can use that condition to work out the fact that you get 3 points of destructive interference in between these two frequencies. You can use that to work out what the original frequency was. Okay. Anyway, sorry, I have to go. I have my other review session scheduled for 4:30. So thank you, everybody, and I will see you tomorrow. Sorry we didn't get a chance to get through too many questions, but yeah, hopefully this is helpful.
Thank you.